Right, so blank is made up of atoms and has mass and volume. We learned this vocab word yesterday. That was absolutely matter. Very good. So perfect. That looks great to me. And in what state do particles flow past each other, filling up the bottom of their container, able to change shape? Yes, that is going to be a liquid. We'll talk a little bit more about that again in just a moment. Plans for the weekend. Let's see here. No plans, being lazy, wedding, clothes shopping, for Bollywood clothes. Oh, that's lots of fun. Crazy. Kaylee, you said you are taking your three little sisters on a coffee date with your best friend tomorrow. Oh, that's so lovely. I like that. Dirt bike with your friends. Oh my goodness, stay safe, Brandon. Online shopping and being lazy. I feel like those two things go hand in hand, right? Looking good. All right, if you haven't already, please go ahead and open up your notes. I did send the link in the chat, so scroll up to find those links. Good morning, Tara. How are you doing? Please remember that in addition to doing your notes just for regular notes credit, that you should be doing them during class if you also want attendance. Remember, attendance is 10% of your grade. You have to actually be here, so I need to see in the attendance report that you're here, and that means that you need to be participating. Otherwise, you won't be able to get attendance. And then you also need to actually be doing the notes. So I do check that the notes are completed during class and that you pass them, because I do give you enough answers to always pass them. So you should be doing those during class if you also want attendance. If you do them after class with the recording, you still get regular notes credit. Just remember, if you also want attendance, you have to do it during class. Okay. Yeah, don't hurt yourself, Brandon. Okay, no worries, Tara. Yes, you got here. You're good. Oh no. Well, Creek, yes, a new food. You still have plenty of time. So as long as you take a picture of some food in the next week, you have plenty of time for your project. Don't forget to write your name next to it, though. All right, so this is a reminder. Please do not share personal information, contact info for your own security and legal reasons. Remember to participate often and well, and make sure you are behaving appropriately. And don't forget that these are being recorded. Excellent, Luca. Yes. Yes. For those of you that aren't familiar with why people are talking about taking pictures of their food, I did send out a recording yesterday that explained how to start your Unit 1 food project. So remember, please do make or buy or have someone make a heated food for you. Could be as simple as ramen or mac and cheese. Again, most people should be able to do this project. If you have an issue, always reach out to me. But take a picture of your food. Make sure your name is written on a piece of paper next to it for plagiarism reasons. Okay. And you should have hopefully gotten a chance to take a look at that yesterday. Again, start your project. If you haven't gotten a chance, make sure to work on it over the weekend. I went over the first 8 slides, so you should be able to work on that. Excellent. Ooh, delicious, Evangelina. All right, so we are on day 4 out of 60. We're finishing up our first week of trimester 3. We're going to be talking about states of matter today. Again, if you did not get a chance to start your project yesterday, please take the time over the weekend to work on that. That way you're not stressed out later for when it is due. Oh, no, no worries, Tara. All right, students, this is a quick announcement that if you are new for trimester 3, our school has some diagnostic assessments called STAR 360, where we test your math skills at the start of schooling and at the end of the school year. So this is called STAR 360 Math and Reading Assessments. But if you're new for trimester 3, you do need a start data point. We need a start point and an end point for you. No worries, Jaden. Glad you were able to make it in. So that means that if you're new for this trimester, which are these 5 people here, so if you see your name down here, then on Monday and Tuesday, you will be required to go to the 1 p.m. session to do your STAR 360 assessments, okay? They're already on your live class schedule, so if you're not sure, just look at your Monday, Tuesday schedule. You'll see them on there. So again, if you're new this trimester, just this trimester, you need to go ahead and, no, you have to wait, Creek. You need to go ahead and do them on Monday and Tuesday. Now, all students will then be required to take STAR 360 at the end of the trimester. Again, new students, you have to do it start and end. That way we have 2 data points to see how you are improving. It does need to be done at the end of the trimester for all of our other students as well. Do not do it now. You have to wait until the end. Otherwise, it does not count for your grade in each of your classes. And it also does not count towards us being able to know how you improved over the entire school year. Okay. These will be proctored during normal classes just because they are because everybody has to do them. So it'll be period 2 in 2 months on May 25th and period 3 for math in 2 months on May 26th. We do not, Umeza. But I think if you want to, you can probably talk to your counselor and they can try to help you figure out where you can go for SAT testing. Yeah, but we don't have a formal SAT testing day at our school. Okay? Yeah, great question. Awesome. All right, so that's just a quick announcement. Again, make sure you check your name down here if you're a new student. Make sure you do your start test, and then everybody will have to do the end test. Okay? Yeah. So let's go ahead and talk a little bit about what we are doing today. We are going to be in our 1C notes explaining kinetic theory and its relationship to molecular motion. We'll be talking about thermal energy versus temperature versus kinetic energy and explaining how energy affects particles when in its single state of matter. So at this point, again, I do need you to go ahead and open up your notes and raise your hand. Here are the links. There is the link if you are in my section, Miss Larkin. Here are the links if you are in Miss Cruz's section right there. And then again, try both links. One will work, one won't. So make sure, again, try both links. If neither of them works for some reason, make sure you're logged into your course and then just go to the grades tab and get it from the grades tab. Yes, garlic bread is a heated food. As long as you have a food that gets heated up, that counts, Evangelina. So just write your name next to it and take a picture of it. And that will work for your Unit 1 project. Great question. All right, keep on going. Raise your hands. I will give you another 30 seconds to raise your hands and let me know that you are ready to go with your notes. Let's go ahead and take a look here. I am going to go ahead and show you a video, all right, of some food dye and different temperature water. So there's going to be warm water on the left, hot water in the middle, and cold water on the right. And I want you to use your eyes to observe what do you notice is happening to the food dye in each of those types of water. So here we go. I'm going to go ahead and share this with you up on the whiteboard. Go ahead, tell me in the chat box what are some observations that you are making here. Again, we have warm water, hot water, and cold water. Warm water, hot water, and cold water. I'll go ahead and I will send out the link too in case you want the link for some reason. There you go. All right, awesome. I see Jasmine, I see Tara, I see Matt in the chat. Let's make sure we're participating. Get your answers in the chat for me. What do you see happening? What do you see happening? Excellent. Yes, yes, yes. There we go. Getting some more people. Yeah, so we definitely see that the cold water is much slower. All right, takes a lot longer for the food dye to spread in the cold water. In which cup is it spreading the fastest? In which cup is it spreading the fastest? Yes, in the hot water. Exactly. Awesome. All right, great observations. We're going to go ahead and jump back over to our playlist here. So let's go ahead and take a look at this. Perfect. Okay, so let's take a look at what we just said. So we said that in hot water, it seems that the food dye moves the fastest or spreads the fastest. Spreads the fastest. Okay, yep, that's fine, Jaden. And in cold water, it spread the slowest. What about in warm water? Tell me in the chat box. So we know what happens in hot water, in cold water. What happens in warm water? Yeah, it was in between, right? Which should make sense, but you never know. There could be some weird phenomenon. So it's important to state that the warm water was in the middle. It was kind of a medium spread. Excellent, excellent. All right, so we're going to go ahead and take a look at what this is related to in just a few moments. But first, we need to review yesterday's topic because we're going to put it all together today. We're going to synthesize all of our information together today. Remember that yesterday we talked about solids, liquids, and gases. We mentioned that solids have definite shape and volume, meaning it does not change. And this is like ice, for example, or frozen water. Frozen water, the ice is very rigid. It stays in place, and the reason is because the particles are just vibrating in place. They're not moving enough to the point at which you can actually see the solid change change its shape. Smiley faces, emojis in the chat box if that makes sense. Okay, the particles are moving too slowly. We cannot see solids change their shape. Beautiful. Now liquids, on the other hand, have indefinite shape but still definite volume. We saw this in our brain stretch today. We said that they can change shape to the point at which they can flow past each other. However, they still have definite volume, which means that they cannot spread out to fill the entire container. They just stay in the bottom of the container. So they flow to fill the bottom of the container. And this is going to be things like liquid water or olive oil or the grease from Creek's Pizza for his project, all right? So the filling up the bottom of the container, those are liquids. Now gases, on the other hand, have indefinite shape and indefinite volume, which means that both can change. Both can change. All right, and this makes sense because the particles in gas are extremely chaotic. They move apart, they spread apart, they try to escape. So for example, if you are thinking about doing something like noodles, well, all of your foods should be heated. So all of your foods should at some point release steam, whether you cook them on the stove or in the oven or in the microwave. All of your hot food will release steam at some point. And so that steam is gaseous water, hint, hint, for your project. And so you can see that steam actually curling and escaping and moving away from your food. It's trying to leave. It moves away from the pot or pan, away from the cup or whatever, the bowl, trying to escape. Okay, go ahead and give me a green check, orange X if all of that makes sense from yesterday. This is what we discussed, talking about solids, liquids, and gases. Excellent. Seeing lots of good and lots of green checks. Yeah, exactly. So you can buy food as well, right? So yeah, you will know that your food got hot enough at some point to steam. If it didn't get hot enough to steam, Kaylee, then it would probably have salmonella in it and kill you. So not kill you, but it would probably make you sick. So it wouldn't be fully cooked. So absolutely, deep fryer counts. Yes. Excellent. All right. So now I do want you to remember that again, even though they're changing what they look like kind of on the outside, chemically they are still identical to each other. So whether water is in its solid, liquid, or gaseous state, it is still chemically what? Reviewing from yesterday, it is still chemically what? What is the chemical formula? Sorry, tell me, what is the chemical formula? Yes, you're right that it's still the same, Tara, but what is that same? Yeah, exactly. It's going to be H2O, right? Made up of 2 hydrogens, 1 oxygen. You can see those exact particles in each of these, right? They are still exactly the same. So the only thing that's changing is how particles are interacting or moving based on how much energy they have. Solids don't have a lot of energy, so those same H2O particles stay in place. In liquids, they have more energy, so those same H2O particles begin to flow past each other. And in steam, water vapor, gaseous water, those particles, those same H2O particles have lots of energy, so they begin to move around chaotically. Excellent. This is going to, let's go ahead and take a look at this on our demo here. So I did want to give you a chance to see all of these kind of in motion. So let me go ahead and share this with you up on the board. Here we go. All right, so let's go ahead and take a look at this. All right, so I am taking a look at water right here. All right, so we're looking at water molecules, and they're currently in their solid form. Take a look there, observe for me. Are the particles moving in the solid form? Are the particles moving, yes or no? Awesome. I see Tara, I see Shane. Yeah, they're moving a little bit, but they're definitely not moving a lot. So this is important to understand that even as solids, they are still moving slightly, but they're not changing their arrangements. All right. So overall, even though they're moving slightly, they're still staying in their same place. And so when we observe ice, it does not look like it's moving because obviously we can't see this molecular motion. It's too tiny for us to see. On the other hand, liquids, what's happening to their speed? What's happening to the speed or motion of the liquids? Yeah, it's getting a little bit faster, right? And so as it gets a little bit faster, you can actually see these particles are kind of moving around. They're flowing around. They filled up the bottom of their container. You did not yet miss any answers, Jaden, so you're good. Just make sure you have your notes open and ready to go. Answer question 1 saying that you understand our attendance policy. Yeah, so they filter down more. Awesome. Now gases, tell me about their motion. Take a look at the gases. Yeah, they're moving way faster. They have way more energy. They're able to spread out. They're moving chaotically. Yes, they're spreading out. They're trying to escape. If I opened this container, they would leave the container. Go ahead and give me a smiley thumbs up or a smiley emoji or a yes in the chat if you feel like this makes a little bit more sense now that you've seen it in action. I know that seeing it in a demo, actually moving, helps a lot. Excellent. Like a toddler on a sugar high. Yeah, someone was like, that's what my brain feels like right now in a previous class. Okay, so this brings us to talking about the kinetic theory of matter. So we've talked about states of matter. Let's talk about why the states of matter are the way they are. This has to do with the kinetic theory of matter, and the word kinetic is a word that you'll hear pretty often in physics and chemistry classes. What it means is it is the motion. The word kinetic means related to motion. Okay, no worries, Nicholas. Thanks for letting me know. Yeah, or movement. Exactly, Tara. So kinetic theory of matter is literally talking about the motion of matter. So it should be very easy for you to remember that definition because it has the word kinetic, you know it has to do with motion. So specifically, it says that the particles in all matter are in constant motion. So constant meaning that they're always moving. And the reason that they're always moving is because they have some energy, some thermal or heat or kinetic energy. Okay, so what this means is that the hotter and hotter you get, the more and more energy you have, and so the faster and faster you move. So gases, for example, are the hottest form of the substance, and so they're the most chaotic, they have the most energy, they're moving the fastest, they're trying to escape. Liquids are not as hot, so they're not quite as fast, but they're still fast enough where they can flow. Particles at low temperatures, though, like in solids, for example, are moving very, very slowly. They never actually stop moving. We saw that in our diagram. They never actually stop moving, but they're staying in place. And so to us, it looks like they are very, very rigid structures. Okay, let's make sure that we fill in number. I apologize. Okay, so here we go. I apologize because this question accidentally somehow got out of order. So we have not yet done 2, 3, 4, or 5 yet. But we are going, this is number 6. So I apologize. This should have been number 2, but it got out of order. So please go ahead and fill in number 6, and then we'll go back to number 2. Great question, Ezekiel. All right, so I'm going to go ahead and give you 20 seconds. Fill in number 6 with the word constant, only the word constant. Capitalization does not matter, but spelling does. So please spell it correctly. Again, this should have been number 2. It's out of order. I apologize. Fill in number 6. Let's go ahead and actually connect this now all to our brainstorms, right? So we've talked about solids, liquids, gases. We've talked about kinetic theory of matter. We did a demo. We saw a video. Let's go ahead and actually put it together now. So what I want you to think about, in hot water, the particles, the food dye, right, spread out the fastest. So what is that showing us? Are those particles moving fast or slow? Do they have a little or a lot of energy? Versus the cold water, the food dye barely moved at all. So that means the particles, were they fast or slow? And based on our kinetic theory of matter, therefore, do they have a little or a lot of energy? Circle the correct answers for each term up there for me. Excellent. Lots of participation. That looks awesome. Yes, you are totally correct. So, yes, the particles in hot water, we saw visually that they are moving the fastest, and they had a lot of energy based on our kinetic theory of matter. This should make a lot of sense because as you get hotter and hotter, the liquid goes more towards the gaseous state, which has a lot of kinetic energy. It has high energy. Cold water, on the other hand, we're getting closer and closer to the solid state, which has very low kinetic energy. So that means it's going to be much slower. It's going to have a lot less energy. These are going to actually be the answers to, if my slides will move, to number 2 and number 3. So again, we just did number 6 because it was out of order. Go back to number 2 and number 3 now. Thank you for being patient, trying to figure that out. You have 30 seconds to fill in number 2. Fill in the blank with the word fast. Number 3, fill in the blank with the number with the word slow. 30 seconds, raise your hands. Go, go, go. All right, so let's talk a little bit about this idea of constant motion, right? We said everything has motion, but we have not yet done number 5, so no. We'll do number 5 in a little bit. All right, so let's talk a little bit about what I mean by constant motion. So there is this theory of absolute zero. So absolute zero, also known as 0 Kelvin. Kelvin is a different temperature unit than Celsius and Fahrenheit. But 0 Kelvin, 0 degrees Kelvin, is where particle motion stops. Now, when I say stop, I don't actually literally mean stop. It's actually at a quantum level, it's impossible for all motion to stop. But it's the minimal motion possible for a particle. So for all intents and purposes, we can say when motion stops or when motion is at its least, when it's moving the least as much as possible, okay? Now, absolute zero, 0 Kelvin, like the Kelvin scale is literally built on absolute zero. Umeza, I can go back to it later. Please, everybody else, don't put answers in the chat. Umeza, just stay after class for a moment and we'll go back to number 2 because I want you to actually see the slide. Okay, so 0 degrees Kelvin is also known in Celsius as negative 273.15 degrees Celsius, or in Fahrenheit, which you're probably more familiar with, is negative 400. Don't put answers in the chat, is negative 459.67 degrees Fahrenheit. So very, very, very cold, okay? Now, the problem is we can't actually reach absolute zero, all right? So absolute zero is actually impossible, at least according to the science that we understand now. It's actually impossible for us to reach. The reason is because as you get closer and closer to absolute zero, you need more and more energy to remove that extra heat. And so at some point, you would need an infinite amount of energy to try to remove all of the heat from a substance to reach absolute zero. Okay, now what I want you to think about, all right, again, is that we've gotten actually really, really close. So we've gotten to below 1 Kelvin on Earth. We've actually gotten to like 100 picokelvins, which is like less than a Kelvin. So very, very small amounts. We've gotten very, very cold. We've actually gotten colder here on Earth than anywhere else in the universe. So the rest of our universe is about 2.73 Kelvin. Really cold, but outer space is filled with cosmic radiation, filled with microwaves, and so those microwaves do cause a little bit of heat. So empty space is actually a little bit warmer than 0 Kelvin. It's actually 2.73. Yeah, it's 2.73 Kelvin, okay? And so we've actually gotten the coldest place in the universe has actually been on Earth. So interesting thing to think about. But anyways, so the reason that it's not possible, all right, to get to absolute zero, besides this idea of energy, is also that if you think about your own freezer at home, does the food in your freezer ever get colder than your actual freezer? Does the food in your freezer ever get colder than your actual freezer? No, right? Because your freezer can only go down to a certain point, and so the food just gets to that point. All right, so same thing with absolute zero. Again, this is not exactly what's happening, but you can think of it, if this helps make a little bit more sense, of like you would need a freezer that's colder than absolute zero to get something down to absolute zero, which is not possible, right? So if that's another way you can think about it, of how this is just not physically possible, okay? So what all that means is that absolute zero is just a theory. It's not a real thing. So in reality, even the coldest particles have some kinetic energy. Again, bringing us back to the kinetic theory of matter, that all things are moving. All particles are moving. That's why even really, really cold solid particles are still vibrating. They still have a little bit of motion. They are not completely still. Give me green check, orange checks if that makes a little bit more sense now of how I say that even the coldest, even solid things still have some motion, because absolute zero is impossible. It is impossible. Green checks if you understand. Alyssa, Seraphim. Thank you, Jazz, in the chat. Excellent. There we go, everyone. Let's keep on moving here. Come on, slides, let me move on. Here we go. All right, this is going to be number 4. Please go ahead and fill in the blank with the word coldest, only the word coldest. You have 20 seconds to raise your hands. Go, go, go for number 4 in your notes. What I want you to think about on the whiteboard, please circle for me. If you have a bunch of people who love dogs, which group do you think would be happier? A group of dog lovers that has 100 people with 20 dogs in total, or a group of 10 people with 20 dogs in total? Who's going to be happier? Go ahead and circle your answer for me on the board, or if you're on your phone, you can always tell me in the chat, who do you think would be happier? Yes, absolutely. I would totally agree. All right, I'm going to pause those tools before it gets too messy. I would agree. I think a group of 10 people with 20 dogs will be happier because on average, each person gets how many dogs? On average, each person gets to play with how many dogs? Excellent. I see Evangelina. Yeah, you get two dogs per person. On the other hand, all right, if you have 100 people and only 20 dogs, you only get a fifth of a dog. Not saying that you actually only get a fifth of a dog because that's morbid, so don't go there. But that means that 5 people have to share each dog. So a fifth of a dog, not actually a fifth of a dog. I'm not advocating for hurting dogs, please, but but just saying that 5 people have to share a whole dog. Dibs on the liver. Oh my gosh, Greek. You're killing me. All right, so this is going to be related to what we're going to talk about, the differences between thermal energy, temperature, and kinetic energy. Okay, so temperature you're probably pretty familiar with. It tells you how hot or cold something is. But temperature is actually what we call an indirect measurement because what it's doing is it's taking the kinetic energy of each of the particles. So the individual motion of each particle, and each particle can have a little bit of different kinetic energy, and it's averaging them. So because it's taking the average, that's why we call it an indirect measurement. Smiley faces, emojis in the chat box if that makes sense. So again, kinetic energy is motion of particles, and if you average all that motion, that's where temperature comes from, how hot or cold something is. Okay, so we'll put that up here, right? So kinetic energy is our motion. Motion, temperature is the average of hot and cold, okay? All right, now on the other hand, this is actually not the same thing as thermal energy, and this brings us why I talked about the dog example. So thermal energy or heat energy is actually a total. It's the total amount of energy you're adding to a substance, okay? But it's not exactly as useful as temperature because, take a look here. Imagine I have a big bucket, which is like a lot of humans, all right? This is like my 100 humans, okay? Versus a small bucket, which is like my 10 humans, okay? Now again, in both scenarios, they got the same amount of stuff. They both got 20 dogs, right? They both got 20 dogs. Big bucket of humans, yes, 20 dogs. Now this is related to thermal energy. So heat or thermal energy is an actual amount, right? So it's a total amount of energy that you're actually adding, okay? So what this is saying is that in both of these scenarios, they got the same amount of heat. They both got 50,000 joules. Just like our people, they both got 20 dogs, okay? But overall, their happiness was different, and in the same way, overall, your temperature is different. So temperature, again, is the actual more useful one because this tells us the actual hot or coldness, okay? So taking a look here, if I have 50,000 joules, but I add it to a big bucket of humans or particles, then on average, each particle doesn't get very much energy. And so overall, on average, you end up not being as hot. You end up being cooler or just warm water, right? So temperature right here, temp is our average, okay? Whereas on the other hand, if you take a look here and you add that same amount of heat or the same amount of dogs to a solution here, to a cup, the cup is much smaller. And so on average, each particle gets more energy on average, even though overall they got the same amount. On average, each particle gets more energy, just like each human got more dogs, and so they end up hotter, or in the case of our humans, they end up happier. Smiley faces, emojis in the chat box if that's making sense. So again, kinetic energy is our motion, temperature is the average of that motion, how hot or cold. Thermal energy is the total amount, but not as useful because, again, it depends on if you're adding to a bunch of water or to little itty bitty water. Okay, perfect. Go ahead and match these up for me on the board. Let's make sure that this makes sense. Go, go, go. All right, this is the answer to number 5. Thermal energy is the total heat added. Temperature is an indirect measure of hot and cold. Kinetic energy is motion. Go ahead, take 30 seconds to fill that out. The last thing I want to talk about is, again, as we add thermal energy, things are going to go from solids to liquids to gases. So we're adding more heat, and therefore their temperature is definitely going to get hotter. And as they get hotter, based on our theory of kinetic energy, that means that they are increasing their kinetic energy on average, and so they get faster. However, this actually also affects the space between particles. Take a look here. Solids, are their particles close together or spread apart? For solids, are their particles close together or spread apart? Yeah, no worries, Kaylee. Yeah, they're going to be close together. So solids are very, very close together, right? And gases, take a look at gases. What about gases? Tell me in the chat box, what do you notice about gases? Yeah, exactly. They're very spread apart, okay? And liquids are kind of in the middle, right? Liquids have a little bit more space. A little bit more space. And again, this should all make sense because based on the kinetic theory of matter, we know that as things begin to move more and more, they begin to spread out. Smiley faces emojis if you feel comfortable with that. That's going to help you with question number 7. Excellent. All right, so I do know that we're out of time. Question number 7 is actually a complete on your own. So let me just explain it really quickly and then I'll let you go. So you need to identify what's going on with shape and volume and particles. Are they flowing, staying in place, or chaotic for solid, liquid, gas? What's going on with their energy? More energy means hotter, medium energy means warmer, less energy means colder. No, Shane, you get partial credit. I always give partial credit on matching. And then if you get, and then what's happening with particle spacing? So which ones have some space, which ones are far apart, and which ones are close together? We just talked about that. Do your best on question number 7. Again, each of these should end up with 3 answers each, 1 from each category. All right, go ahead and do that, and I will see you all later. Don't forget to answer that last question number 8 of just saying that you understand that you need to do your projects. Thank you so much, everyone. I will see you later. Take 30 seconds to log on out. Make sure you finish this one up. That way you can get your attendance for doing your notes in class.